We are building off the last video. If you remember, what did it end with? Well, it was called approximating polynomials. And I mentioned we were going to use this and build upon it to try and approximate more general functions, but it ended with, we would take a polynomial, okay? And then you can rewrite it as a polynomial centered at a by the coefficient. Let's say the coefficient in front of the x to the k. We took the kth derivative, evaluated at a, divided by k factorial. And this was the coefficients of this. Well, it was just a way to rewrite the polynomial with the difference center. Okay, now we are talking about Taylor polynomials. Let me begin with the definition, and you will see it's going to look exactly like that. And that's really why we started with this section. Okay, definition. The nth order Taylor polynomial for some function, for f of x, and centered at a. And what I am defining here is everything I have written. So I'm defining nth order Taylor polynomial for f of x centered at a. Well, first of all, what's the notation? The notation is like this: t upper n lower f x a. Okay, this is our text notation. This is notation. And you could also see it elsewhere. Other notation, you might just see t sub n of x, like this. I've seen it like this in other texts. This notation, for example, doesn't show the function, doesn't show the center. So in a sense, this is a little more complete as we see it in our textbook because it has, well, everything that's referred to in the definition. Well, what is this? Okay. This is a sum k equals 0 to n. We take the kth derivative of the function evaluated at a divided by k factorial times x minus a to the k. This is exactly what we saw in the last one when we were rewriting a polynomial as a polynomial with a different center. Okay? But here, f can be any function. Well, as long as you can differentiate it in time, so it has to be n times differentiable for this to make sense, but it can be quite complicated, and we still have this Taylor polynomial nth order for f centered at a like this. Now, a very special case, maybe I will erase this other notation, a very special case which comes up a lot is when a equals 0. This is called the Maclaurin polynomial, called, well, I will include this, nth order Maclaurin polynomial. Okay, so this is when you are centered at 0. It's the way we normally look at polynomials, for example, and how I started last time. I just started with a normal in the sense of how we're used to looking at polynomials, where you have x to the k times some coefficient. This is the Maclaurin polynomial. We would evaluate the kth derivative at 0 divided by k factorial, or the coefficients, and then it's just an x to the k, like this. Okay, well, what's the idea behind this? Why are we studying these things? The idea, let's take n large enough. The idea is that this nth order Taylor polynomial should be a good approximation of the function nearby the center. Okay? And certainly, if you remember from our discussion last time, the first order Taylor polynomial, it's going to be exactly the tangent line, and that's something that you discussed in Calc 1, for example. And as you go to higher order, second order, third order, you're just getting a quadratic or a cubic nearby x equals a. So this is the idea. And how good of an approximation is this? That kind of thing comes with, well, next when we start talking about error. But this is the idea. This is why we want to study things. And generally, a function is complicated. A polynomial is not complicated. Okay, well, let's do some examples. I'm going to if you remember last time I did 2 examples at the very end where I made a little chart where I had k, the kth derivative evaluated at the center, and then kth derivative evaluated at the center divided by k factorial. I do the exact same thing every time I find a Taylor polynomial using the definition. So let's consider f of x is e to the x, and let's find the, let's say, fourth order Maclaurin polynomial. Okay, well, this one is going to wind up being pretty, well, simple, I should say. It's going to be easier than the polynomials we were doing last time. Okay, I take the kth derivative. This is Maclaurin, so I evaluate at 0 over, well, first I just do this, and then I make a column for the kth derivative at 0 over k factorial. And then when I have done these, here are the coefficients of my polynomial. They should be numbers. Okay, now, then I want fourth order, which means I need to go up to k equals 4. Okay, well, the derivatives will be pretty fast because look, my function is e to the x. What's the derivative of e to the x? E to the x, differentiate again, e to the x, differentiate again, e to the x, and e to the x. That's my favorite part of this problem. Because the derivative of e to the x is e to the x. Now evaluate at 0. E to the 0 is 1. So we get, look, 1, 1, 1, 1, 1. They're not all this easy, I should say. This is our first example. Now I divide by k factorial. So I have 1, 1, 1 half, 1, or maybe I'll put the factorials, and 1 over 4 factorial. Of course, I could simplify these coefficients if I wanted to. This one is a half. 3 factorial is 6. And 4 factorial, well, it's 4 times 3 factorial. So this would be 24, for example. And then, maybe I'll put it at the bottom. It's fine. So this notation, it's t upper 4 f x. I'm centering at 0. Well, it's 1 plus 1 times x plus 1 half x squared plus 1/6 x cubed plus 1 over 24 x to the 4th. This is my Maclaurin polynomial for e to the x, fourth order Maclaurin polynomial, or equivalently, another way to say this is Taylor polynomial centered at 0. Now here's another example. Again, Maclaurin polynomial. After this one, I will do a different center, but we want to find the fifth order Maclaurin polynomial for f of x is the sine of x. So we need the kth derivative at x. We need the kth derivative at 0. And then we need the kth derivative at 0 divided by k factorial. Okay? And we want fifth order, which means we have to keep computing derivatives until the fifth derivative. Well, this won't be quite as quick as with e to the x, but it's just sines and cosines every time I differentiate. So my function is the sine. I differentiate sine, positive cosine. You differentiate cosine, negative sine. Okay, now you differentiate, well again we're differentiating sine as positive cosine, but we have a minus. We differentiate again, we have a negative sign with a minus, so this is positive sine. And finally, the derivative of sine, one more time, cosine. You can imagine, and we will get to this, you can imagine just keep going forever. And this one will go sine cosine minus cosine, sine cosine minus cosine, like this. Whereas the first example, if we kept going forever, we would just have e to the x forever in terms of every derivative. Keep differentiating, keep getting e to the x. Okay, well, now let's evaluate at 0. The sine of 0. Oh, we have to think for a moment. Let me draw. We are evaluating here where the sine is 0, but the cosine is 1. Okay, that's all we need to know to evaluate all of these. It's just what's happening at x equals 0. The sine is 0, the cosine is 1. The sine is 0, the cosine is 1. The sine is 0, the cosine is 1. Now divide by k factorial. These will be the coefficients in my Maclaurin polynomial. 0, 1, 0. This one is 3, so minus 1 over 3 factorial. This one's 0. This one's 1 over 5 factorial. Now, let's write our polynomial. Where am I going to do it? I'll write it, oh, in fact, I have plenty of room. Write it over here. Okay, because you see, I only have 3 terms that are non-zero. 1, 2, 3. So my polynomial, which is t 5 f x 0. This is with our notation of our textbook. This is, well, I have x, I have minus x cubed over 3 factorial. I have plus x to the 5th over 5 factorial. Like this. This is our 5th order Maclaurin polynomial for the sine of x. Here, maybe I'm covering it. It's here. Now we'll do 2 examples of Taylor polynomials with different centers, and then we will look at some graphs in Desmos. Okay, the first one is this one. We want the 3rd order Taylor polynomial for the natural log centered at 2. So I'm going to make my chart. My center, oh, maybe I should have written centered at a equals 2, but it's fine. My center is 2, and I'm going 3rd order. So when I make this, I go 0, 1, 2, 3, and then I have the kth derivative at x, the kth derivative at 2, and then the kth derivative at 2 divided by k factorial. Okay, well, this is the function. Now I start differentiating. Derivative Natural log, 1 over x. I'm going to write it this way because I'm going to differentiate more. Differentiate again. Minus x to the minus 2. Differentiate again. 2x to the minus 3. Well, now my center is 2. So I don't want to evaluate these at 0. In fact, my function is not even defined at 0. I evaluate them at 2. So here I have natural log 2. This is 1/2. Here, this is negative 1 over 2 squared, which is going to be 1 over 4. And here, this is a positive, well, it's 2 over 8, which is simplified 1 over 4, okay? And then one more step, I divide by k factorial. These will be the coefficients in my polynomial. Okay, so I have ln 2, 1/2. Now 2 factorial is 2, so this is negative 1/8. Here I divide by 3 factorial, which is 6. So this is 1 over 24. Okay. And now I am ready to write down, my polynomial. Maybe so I can put it on one line, I'll do it at the bottom. So this is t, 3f, x, 2. Okay, so I have ln 2 plus, I have a half. Now, don't just put x because my center is 2. It's x minus the center, and then plus. Oh, well, it's going to be minus because my next coefficient is negative 1/8. So minus 1/8, x minus the center squared, and then plus 1 over 24, x minus the center cubed. Okay, this is the third order Taylor polynomial for the natural log of x centered at a equals 2. Okay, now let's do one more. Then we will look at some pictures. Let's find the fourth order Taylor polynomial. We will do the sine again, but I will change the center. Okay. Well, the derivatives I've actually already computed, but I'll rewrite them because I don't have them on the board at the moment. And then, now, this will change. I evaluate these functions at pi over 2 instead of at 0, and then I take the kth derivative at pi over 2 over k factorial. And I want fourth order, 0, 1, 2, 3, and 4. We start off with the sine. I'll do this a little faster because we did it already. Derivatives cosine, derivative negative sine, derivative negative cosine, differentiate again, positive sine. Okay, we did that already, right? It's just the fact that the derivative of sine is cosine, derivative cosine, negative sine. Okay, now I need to evaluate at pi over 2, which pi over 2, if I redraw my unit circle, it's here, pi over 2. Okay, so the sine is 1, cosine is 0. So this means this is 1, 0, minus 1, 0, 1. Okay, now I divide by k factorial. This is 1, 0. This is negative 1 over 2, 0, 1 over 4 factorial, like this. I could multiply this out. We would get 24 as we did before. I could also leave this as 2 factorial. It's fine also. So now let's write this fourth order Taylor polynomial. Maybe I will do it down here just because I have a little more space. Okay, so this is t. This is fourth order f x pi over 2. Okay, we have 1, and then we have a minus 1 over 2 factorial, x minus the center. This is 2 squared. And then this is 0, 0. We have this term, which is a plus 1 over 4 factorial, x minus the center to the 4th. Okay, so this is the degree 4 Taylor polynomial for the sine centered at pi over 2. I have made this little Desmos tool. Unfortunately, I cannot get it to display these Taylor polynomials, but let us, no, I have the wrong I want to go to a equals 0. So I want to look at a few of the examples that we just calculated, and we will see, for example, this first order Taylor polynomial, well, is the tangent line, and then we will see the second order. Well, let's start looking. Here is the tangent line. Here's e to the x at x equals 0. This is the one where all the derivatives were e to the x. Okay, and we went to order 4, I guess, in our calculation. But you see here, looking at this graph, maybe I can zoom in a little. Okay, you see here, looking at this graph, that this is a linear approximation. Okay, this is the tangent line. But then you see, now I have to zoom out so you even see how it, well, you see a little down here differs from the function. This purple is the second order Taylor polynomial for e to the x, or Maclaurin, I should say, because we're centered at 0. And you see, if we zoom out, the purple versus the black, which is our actual function, far away they are not that close, but nearby the center 0, in fact, it's a better approximation than the tangent line. Similarly, if we added, now the blue is a cubic, it's degree 3. This is the third order Maclaurin polynomial. And again, we zoom out and we realize it's not that great of approximation far away. Okay, we can keep adding. This is the fourth order. Now, in fact, let's take away everything but just degree 3, degree 4, and the function, which is in black. Degree 4 is in red. So again, degree 4, the approximation improves, at least from our visual eye, right? The next topic we will do is we're going to calculate the error bounds and see it like this. So we'll be able to say something more precise about how close these approximations are nearby. And then finally, you see degree 5. But, you know, e to the x is not a polynomial. So none of these will match up exactly to the whole function, for example. Okay, well, let's look at another one. So maybe I will, what else did we calculate? We did the sine x. Okay, here's the sine, x equals 0. And then we did, here's tangent line, but you notice this didn't change because we found that the even powers, the kth derivative at 0, the even ones were 0. And then here in blue, this is the third order Maclaurin polynomial. Then in red, it's the same thing because we don't have another derivative here. This will be fifth order. Well, these all look really different. But if you zoom in, we are approximating the sine, SINE, at x equals 0. And you see, now you see, let me take off the ones that don't add anything. This one and this one. We only have odd powers once we evaluate the derivative at 0. So here we see the first order, third order, fifth order. Maybe I will add. There's the tangent line. There's the blue. This is degree 3. It's a better approximation. And then this in orange is degree 5. Okay, for example, we see we are approximating the sine nearby x equals 0. Now, I don't think I can switch this to pi over 2, which we did that example. So let me just finally look at the last one we did. We did the natural log. This one we did at center 2. So I need to come over here. And this one we had all of these. I forget how far out we went, but you can look at some of these. So here, centered at 2. We see the tangent line. There is the point. Maybe I could graph the point also. Let's graph the point 2 comma natural log 2. Okay, there it is. We have it on our graph. And then we can do the second order. And the approximation nearby, x equals 2 gets better. Third order. These are all polynomials, fourth order. And we are getting better. But if you zoom out, natural log is not a polynomial. You see, the natural log is which one? It's the black one. None of them are very good approximations far away, right? You see, very far away when we get to even here, for example. None of them are anywhere near close. But the point is, we are trying to approximate nearby the center. Okay, I like this. I hope this was good illustration. And now we will go back to the whiteboard. Let's make a few comments. First of all, and I have discussed this, the first order Taylor polynomial for a function centered at x equals a. Well, this is what we've been started with the last time that really motivated, sort of have a polynomial, write it as a polynomial centered at something else. So the first order, well, this would be T1, F, X, A. This part is not as enlightening as what it actually is, which is the following. It's f of a plus f prime of a times x minus a. Well, this is the tangent line. Okay, that's an important comment to write and think about. Now, second comment, in the examples we saw, we could keep differentiating. I'll say differentiating. Differentiating. Okay, I had just enough space. Forever, and I mentioned this, you keep differentiating e to the x every single time, e to the x. Okay, keep taking derivatives. You keep differentiating sine. You alternate between, you go what? Sine, cosine, minus cosine. Sine, cosine, like this, spirals, but you could keep doing it. Even with the natural log, you can keep differentiating, and the powers of x will just march down, right? First we have an x to the minus 1, minus 1x to the minus 2, positive 2x to the minus 3. Keep differentiating, okay? And this leads to, or motivates, I should say, this definition. A power series centered at A is, well, it's the following. It's a sum k equals 0 to infinity of ck x minus a to the k, where ck are just some coefficients. Okay? Now, this is, you can think about this as being some sort of formal expression. Think about it as being a polynomial that has no, say, highest degree. You just keep having terms like this. Okay, now, a caution, we don't even know much about this yet. And for instance, what values of x does this converge? Meaning, what values of x is this a number, right? For a polynomial, you evaluate it at some x value, you get a number for every x, okay? It's just finite degree d, number of, well, degree d plus 1, number of terms. But you just have a finite number of terms, you evaluate them, you get a number. Something like this is not obvious that you evaluate this at some x value and you get a number because you think about this as being this, you're adding up infinitely many terms. But for the moment, I'm just using this as a formal way of writing down what is a power series. It's a sort of infinite version of a polynomial where you keep adding. There's no sort of highest degree. Okay, it's certainly something we can think about, and the mathematics of which will come in the, well, to come. We will do more videos and learn more material and things like this. But this is what a formal power series is, okay? And there are, you can imagine, the power series that we are interested in right now, definition number 2, the Taylor series. For f of x centered at x equals a. What's the notation here? We have a t, f, x, a, just like with a Taylor polynomial, except instead of putting an n, we put a infinity. And this is, instead of going k equals 0, to n, that would be nth order, I just keep adding forever, okay? If we can keep differentiating forever, as we can with e to the x, sine and cosine, okay, we could write this down, okay? And again, when a equals 0, this is the Maclaurin series. Okay, but for the moment, we are going to just try to compute. So let's do an example that we actually already did. Let's take f of x is e to the x and find the Maclaurin series. Now, instead of rewriting the whole table, because I did that at the beginning of this video, we know the kth derivative at x is e to the x. Oh, I wrote e to the, oh, goodness. e to the x, okay. I had k. At least I was keeping with the same thing I had written above. I meant e to the x. Now we're okay. The kth derivative of f of x is e to the x. And I'm differentiating with respect to x. It's e to the x. Okay. And so the kth derivative at 0 is e to the 0, which is 1. The kth derivative at 0 over k factorial is 1 over k factorial. Okay? I could do the whole chart again, but as I mentioned, we did this at the start. And all the derivatives are the same. They're all e to the x. Okay, well, if we write this, well, we can start writing out the terms when k equals 1. In fact, this was our polynomial. Well, we have 5. Okay, it's fine. But it's much easier, in my opinion, just to write this in summation notation. It's x to the k over k factorial. This is one that this converges for all x. I will talk a little bit about the convergence of power series like this. Or at least I will talk about when does it equal the function a little bit now, and then we will come back after we discuss all the tests for series of numbers to talk about power series convergence. We'll have a radius and an interval of convergence. That's coming later in the semester. But this is one where this, I will just say as a comment, literally equals e to the x for all x. The infinite sum. So not if you cut it off and do some finite sum, e to the x is not a polynomial, but the infinite sum, it equals e to the x. So in particular, you might have seen this before, then I'll do another example. In particular, e itself, this number e, which we know is 2.71 and change, right? It's in between 2 and 3. This is literally equal to this. This is e. It's pretty crazy to think about, but this is e. This is the number e. Okay. This is not all that different than e to the x. 2 to the x is still an exponential, but it has a different derivative. The derivative of 2 to the x is not just 2 to the x, but I will work to find the Maclaurin series, and I will practice writing in summation notation. And I think for now, so we have a lot more series to come. Right now I'm just kind of introducing the idea. Then we're going to talk about error in Taylor polynomials. But so this will be the last one that I do using the definition. Okay, then I'll make a comment at the end. Okay, so let's find the Maclaurin series. So what we need to do here, I will write this one in summation notation. We just have to compute enough derivatives to find a pattern. But if you don't like summation notation, maybe find 5 non-zero terms, something like this, and then put ... as I mentioned. Okay, well, this is 2 to the x. Ask yourself, what's the derivative of 2 to the x? Well, any exponential, it's ln. If you have a to the x, the derivative is ln a times a to the x. We differentiate again. Well, what happens here is the 2 to the x, we have an ln 2, right? And then we differentiate 2 to the x, and we get another ln 2 times 2 to the x. So we're going to have this times 2 to the x. Okay, then we differentiate again. Well, we're going to have the ln 2 squared, and then we differentiate 2 to the x. Well, then we get another ln 2 times 2 to the x. So this becomes cubed 2 to the x. One more time, and then hopefully we can see the pattern, because what I need to see, because I personally like summation notation, it's easier. You just have to write one term, the kth term. So we do it one more time. We differentiate. This is the constant. When you differentiate this, you get one more ln 2. Okay, now let's evaluate at 0. 2 to the 0 is 1. So we get 1 ln 2 quantity squared, ln 2 quantity cubed, ln 2 quantity to the 4th. Now we divide by k factorial. We have 1, we have ln 2 over 1. Okay, fine. We have ln 2 quantity squared over 2 factorial. We have ln 2 cubed over 3 factorial. And then we have ln 2 to the 4th over 4 factorial. Now, this is 5 non-zero terms. I can certainly write out the terms for my Maclaurin series and put ... t infinity f of x 0 would be, we have 1 plus ln 2 times x plus ln 2, squared over 2 factorial x squared. I mentioned I would do this in summation notation. I will momentarily. Okay, first I'm writing out the terms, and you can choose how you leave your responses. So this is ln 2 cubed over 3 factorial x cubed plus ln 2 to the 4th over 4 factorial x to the 4th, like this. This is one way you can write a power series by putting the first 4 or 5. I would read what it asks for in the problem. Non-zero terms followed by ... Now, what else can I do? Well, this is pretty straightforward, I would say, to see the pattern. I can write this in summation notation. Okay, what do I have? I have an ln 2 to the k. I have an x to the k over k factorial. You see? And it even is okay with k equals 0, because anything to the 0 is 1. X to the 0, 1. 0 factorial, 1. Right, I mentioned that, and it must be. Okay, so this is another way to write the exact same thing in summation notation. I personally prefer summation notation if I'm writing something, because I only have to really work with one term. Write one term. Here I had to write 5 different terms. Here I just write a sum, and then I write the kth term. Okay, so this is an example of computing the Maclaurin series. Let me make one more comment. Well, we see, I'll make the comment right now with this on the board, then we will be done. This is the Maclaurin series. If we take a Maclaurin series or a Taylor series with some other center, and we take, remember we were talking about this, the partial sum. So if we take the partial sum, which means we cut it off up to, let's say here, degree 2, the partial sum of order 2, well, this is the Taylor polynomial, okay? And this is general. If you take a Taylor series, which just means for the moment you just keep differentiating, you keep adding these terms, and we worry about convergence, things like this later. But then if you take and cut it off at some degree, right here would be degree 3, this would be here, this would be T3, maybe I'll write it underneath. This would be the Taylor polynomial, so the partial sum coming from the Taylor or Maclaurin series, for instance, to here, this is T3Fx0, and this is the partial sum of order 3. And this is generally the way it works.